Good evening, everybody. I'm Chris McEntee. I'm the Executive Director and CEO of your American Geophysical Union, and I am so delighted to be here to welcome you for the kickoff panel for this year's Data Fair activities. Before I say just a few remarks and then turn it over to Erin Robinson, you know, we get a little lonely up here, so if you're comfortable, could you move a little bit further to the front? So it's okay if you can't stay the whole time and leave, but we'd love to have you kind of crowd down here if you're open for that. We would appreciate that. I think you all know that AGU's data position statement affirms that data are world heritage. AGU's commitment to open data and data stewardship dates back 20 years, so that's 2 decades, to when AGU developed its first society statements on open data. Through programs like this data fair, we, along with our members, promote data skills, tools, and best practices to benefit our members and their organizations, and more importantly, the advancement of science and the ability to have credible and reproducible information as evidence for policymakers to make sound decisions. This year, AGU and many partners were awarded a grant from the Laura and John Arnold Foundation to implement across the Earth and space science community policies and guidelines that enable fair data. This means that through this effort, we will be striving to make sure that data sets that support scholarly articles will be open and follow the FAIR, that's capital F, capital A, capital I, capital R, guiding principles of findable, accessible, interoperable, and reusable data. This session on emerging and developing data sources kicks off a week of activities around open data at this year's fall meeting. We are again working with the Earth Science Information Partners, ESIP, to help organize and conduct this week's session. And I really want to thank Erin Robinson, ESIP's Executive Director, for developing such an interesting and engaging set of panels for our community. Later this week, I hope you will be able to stop by town halls on data planning on Tuesday. On Wednesday, there's a session on building data capacity. And Thursday, there's a session on author and reviewer data management best practices. We will be giving away an Amazon Alexa to someone who asks a question during each session. A little enticement never hurts, particularly as it gets to be Wednesday and Thursday of the meeting. In addition, you can go to a data help desk in the poster hall next to the AGU publications booth starting tomorrow. There you will find demos, workshops, and support for the reference desk, including how to help with the data management plans, finding a repository, and tools and resources about managing your data to a very high quality. I hope you'll take some time to meet the members of our informatics community, or what we call ESI, at AGU, and the tools and capabilities that they want to make available to you and all our AGU members. Tonight, I think you're going to hear from a very, very engaging group of our speakers. They're going to share their work with emerging and developing data sources that are having a significant impact on our society. This includes data generated from drones, CubeSats, and the expanding community of citizen science. Please join me in welcoming our panelists and our moderator, Erin Robinson, the Executive Director of ESIP, and thank you, Erin.
Thank you so much, Chris, and welcome everybody to this year's Data Fair and to the kickoff panel on emerging sources of scientific data. As Chris said, I'm Erin Robinson. I'm the Executive Director of ESIP, which is a federation of about 100 organizations that are coming together around earth science data and technology challenges with the mission to make data matter. And I want to reiterate just a few of the things that Chris said. And so I'm so happy that she gave the context for why AGU cares about data. And it's been really, I think, an amazing thing that AGU as a society had a position in 1997 on data as a World Heritage Object. And she mentioned ESSI, which is our community of Earth and Space Science Informatics. And so AGU had the position statement in 97. ESSI officially started with a lot of people that are still here, including Peter Fox, who some of you may know, and Kirsten Leonard and Jens Klump were also part of that mix, as well as Robin Fist. And so over the last really 10 years or 12 years, ESSI has just flourished. And so in 2015, we had the first data fair, and it was just a small event in the exhibit hall, a couple of panels. Last year, we really made it more practical to the scientists. We raffled off drones last year as another enticement, and came up with these resources that you can go back and look at for researchers about how to make data matter in your work and how to do more with data. And then this year, this is the largest ESSI program that we've had. I was just asking Ruth Dewar, who's in the back and is the president of the ESSI focus group, and she said that there were 729 abstracts, there are 40 sessions this week, and there are 4,200 people who claim ESSI as either their primary or secondary affiliation. And just, I'm curious, a quick show of hands for who claims ESSI in the room. Anybody? Any ESSIers? That's good. It's actually, I'm happy to see a nice mix, because really one of the things that has emerged out of ESSI and out of this data fair activity is that data is not a specialty track. And it's not something that some of us do, it's now something that all of us do. And it turns out that we need to manage, analyze, and share it so that data skills are becoming these critical job skills. And so the data fair, the data help desk that Chris mentioned, are all things that we're trying to do to build the capacity of AGU as a whole. So this is just, we'll gloss through that, the data help desk. So really, what I want to get to here is that the panels are supposed to be participatory. You all aren't here to listen to us just chat at the front and talk at you. And really, it's about how to make this useful for you. And so tonight we'll be curating questions with Slido. Each panel will have its own hashtag, so please tweet to AGU Emergent Data with your questions. And then at the end, we'll go through a set of moderated questions. And if you go there now, there's actually a poll to get you started to see what you're most interested in. No pressure to our panelists, but I'm curious about where the room is on CubeSats, drones, and citizen science. So with that, I'll introduce our panelists. And I'm going to introduce all three, and then they're going to come up, and each of them will give about 10 minutes of remarks, and then we'll turn it over to the Q&A. So first up is Joe Mascaro from Planet, and Joe is a tropical ecologist, and he's director of the academic programs at Planet, which is a San Francisco-based aerospace company that operates the largest fleet of Earth imaging satellites, or CubeSats, and they currently have just over 150, and I'm hoping that Joe may correct me with the actual number. Joe works with universities and individual investigators to utilize Planet's unprecedented imaging resources to enhance primary research and education, improve forest monitoring and conservation, expand food security, and promote ecological resilience for some of the world's most vulnerable communities. I'm really excited to hear about how we might be utilizing CubeSat as, or CubeSats as an emergent data source. I'm not sure what's going on out there. Next up, and coming down in the atmosphere, we have Robert Moorhead, who is currently a distinguished professor in the Department of Electrical and Computer Engineering at Mississippi State University, and he's also the Director of Geosystems Research in the Northern Gulf Institutes at Mississippi State. Over the past 8 years, he's developed an applied unmanned aerial system, UASs, program focused on precise agriculture and natural resources. And his current research interests include computationally demanding visualization and analysis issues using usability of visualization systems, and applied visualization. And then finally, getting to the emerging data trend of citizen science, we have Julia Kamari-Drapkin, who's the executive producer and founder of ichange.org. She's a radio and television and multimedia producer based in New Orleans, with a passion for finding innovative ways to connect people to their environment and to each other. IC was born out of covering natural disasters and climate change science across the globe and in her own backyard. Her work with IC Change has aired on This American Life, won several national and regional awards, and has been recognized by the White House Climate Data Initiative. Prior to journalism, Julia did research, anthropology, and archaeology for over 7 years in Latin America, where she geeked out on Mayan farmers' almanacs. I'm so excited to welcome all three of these speakers to the stage, and with that, I'll turn it over to Joe.
Thanks very much. Appreciate you guys hosting us, and I'm really delighted to talk to everyone about Planet. Before I even start, on the chance that I forget, Planet is running a town hall as well tomorrow at 12:30 p.m. It's called Earth Science in Real Time, so you can find that on the calendar and come hear from some of our actual users. So I want to tell you about what Planet does, and I want to start with just a contrast of kind of classic aerospace. So this is Landsat 7. It's relatively typical of large government-funded spacecraft. You can see there it's about the size of a small bus. I want to talk to you about another mission which encapsulates some of the challenges of running this type of large-scale and often slow-moving aerospace development. And that's the Orbiting Carbon Observatory. OCO was selected by NASA in 2002. And that's basically NASA saying, okay, we think this is the right priority for the agency and for the collection of scientific data. And it took 7 years for a launch attempt to be made, and that was on a Taurus rocket. And that launch attempt unfortunately failed. The fairing failed to separate, so it crashed in the ocean. And then its follow-on replacement, OCO2, was authorized the next year, and then it eventually launched 5 years later on a Delta II rocket. Now, the first iteration cost about $275 million, including the instrument and the rocket. And the second one, they kind of upgraded the instrument a little bit, and they also upgraded the rocket, and that out the door was about $500 million. So about $750 million on one mission. The timeline in the background that I'm showing you is actually the CO2 concentration of the Earth's atmosphere. So just in the 12 years from the creation or the decision to execute what we deemed a societally vital scientific observation from the atmosphere, to actually get that vehicle into space to start its primary mission, took 12 years. During that time, 25 parts per million of CO2 were added to the atmosphere, or essentially 1/5 of the human-caused portion of CO2 in the atmosphere. At Planet, our mission is to image the entire world every day, making change visible, accessible, and actionable. This mission is different than OCO. I'm just making an analogy there. But I want to contrast us with OCO for the simple purpose of looking at what we've accomplished in a very short period of time. Planet was founded about 7 years ago. I can't actually give you an exact number of satellites in space. There's a couple reasons for that. We're using some of our older satellites are in the orbit of the space station, and they are in the process of deorbiting. So we have 150 in sun-synchronous orbits right now, and then there's a few more in the orbit of the space station. We actually have a Dove attached, on board the Electron flight that is scheduled for, I believe, they just updated, is scheduled for 7 p.m. Pacific time tonight. So if you want to try and catch the launch of a Dove, you could do so actually this evening. We acquired the Rapid Eye constellation of 5 sun-synchronous imaging satellites in 2014, and then this year we acquired the Terabella team from Google, and that included 7 spacecraft that were already in space and 6 that were launched just a couple of months ago on a Minotaur C rocket out of Vandenberg Air Force Base. But Planet's core history as the Planet Labs company only goes back, as I said, 7 years. When you're in Silicon Valley, you have to have a garage photo of how your company was created, and here indeed is that garage photo with our 3 co-founders and several members of the team, many of whom are still with the company. This is the satellite that we've developed for our effort to image the entire Earth's surface every day. It's called a Dove. It's a 3U CubeSat. It's 10 by 10 centimeters by 30 centimeters. And although we're on design iteration 13, many of the early iterations of the Dove included a lot of off-the-shelf technology, and the current design iteration still does use off-the-shelf technology for some components. And I'm talking about solid-state drives, batteries, and so forth. We were able to iterate in a way that was incredibly rapid compared to classic aerospace, and that's basically the founders intended to design, build, test on the ground, and then launch as quickly as possible, test in space. We could fly as cargo often to the International Space Station, so that was a quick way to get to orbit, test in space, fail quickly, and learn from those failures, and iterate new hardware. And that's how we've pushed through 13 full design iterations of this spacecraft, which is now a very mature, very reliable spacecraft. Our manufacturing facility in San Francisco can put out 20, actually even sometimes 28 Doves in a single week when we're in manufacturing mode. We've launched 14, hopefully tonight it'll be 15, successful launches deploying over 200 Doves into space. Again, older spacecraft were in the space station orbit and have since deorbited. We operate a large ground station network that brings this data back to Earth. Here's what one of these launches looks like. Earlier this year, we launched 88 Doves on a single rocket called a PSLV out of India. That's got some solid motors attached to it, so you notice it really rockets off the pad. This was a great launch for us that basically brought us pretty close to mission 1, this ability to image the whole land surface of the Earth every day. And later that year, we actually took images of the launch of another 50 satellites from a Soyuz vehicle. This is going to slow down. If you look in the center, you'll see an orange plume. That is the Soyuz rocket. This is not strictly a video. This is cobbled together from frames of Dove images. So we commanded the Dove to point at a fixed location on the Earth's surface, Baikonur Cosmodrome in this place, and then we stitched those frames together into a time series. This is what the orbit looks like generally. So we're inclined in a typical sun-synchronous orbit, but we have 100 satellites in one, and we have another 50 in a related orbit that's just inclined in the other direction. Both have morning crossing times, and as the Earth rotates underneath, just like mowing your lawn or driving a Zamboni, we collect the data. I'm going to blow through. I'm looking at the clock, and I realized I overbuilt a little bit of this, so I'm going to actually skip ahead. I want to talk to you about 2 major initiatives that Planet is doing with the data, and these are probably, generally speaking, among the key ways that members of the AGU community would be able to access our data. The first of those is our disaster response program. So if you go to planet.com/disaster data, you will see various data releases that we've conducted, often in direct coordination with the UN Space Disaster Charter, which we're a contributor to. Oftentimes, there is also media interest depending on those particular disasters. Just this week, there was a Reuters piece using Planet Imagery to analyze large refugee camps that are growing in Bangladesh. This is just over the course of 3 months. This is a Planet Dove image on the right, and this is one 3 months later that shows a radical expansion of these unplanned settlements. We're also able to use the high-resolution SkySat imaging system to look at these in greater detail. And in this case, Human Rights Watch and other organizations were able to analyze high-resolution data from this area in order to figure out how to do emergency efforts to improve sanitation and other engagements on the ground. Here's some imagery. This is actually shown in our Planet Explorer. This is the tool that people use to browse planet data. It's a GUI, it's a graphical user interface. It's built on top of our API, which is how we serve the data. In this case, you're seeing before and after of Hurricane Irma on the British Virgin Islands. So the green image is when they were totally forested, and the dark brown image is when the leaves have been stripped off the tree, basically. Again, we can swing in the SkySats and look up close to do damage assessment on individual buildings. Here you see also a lot of debris in the water. And the last program, and then this is the one we'll talk about extensively in the town hall tomorrow at 12:30, is our education and research program. We launched this in April. We have approximately 1,000 users. We're trying to build the community. At the moment, there's only a handful of people at Planet that are working on this, basically myself and one other person. So we're kind of moving as quickly as we can, but we're a team of two, basically. And we can now take applications from anyone at a university to access Planet data for non-commercial research purposes. So if you go to go.planet.com/research and you are at a degree-granting university, we can enroll you in this program to power your research. The license that comes with it essentially enables you to do all the manner of research activity that scientists normally do, publishing papers, attending conferences, etc. I'm not going to zero in on each of these, but these are some early results of peer-reviewed manuscripts that are now incorporating Planet data, working on all manner of things, especially agriculture science, where our dense time series allows the exploration of data in agriculture surfaces at a daily pace. We're looking at coral reefs, we're looking at glaciers. A couple of quick examples. Sarah Cooley, who's here this week, she's giving a talk of her own and then also speaking at our town hall tomorrow, is using Planet data to study Arctic hydrology. And because we're imaging the Earth every single day, she's able to build incredibly dense stacks of time series data in order to look at dynamics of hydrological systems in ways that people have never essentially seen before. Similarly, we've got people working in smallholder agricultural yields in this case, East Africa. And in this case, we're able to use those high-resolution assets where you can get down into sub-field detail, even for smallholder farmers where their agricultural land holdings are often only 1 or 2 hectares. And this is my last slide. This is an example from coral reefs with Greg Asner and Robin Martin from the Carnegie Institution for Science. We studied the dredging operation that's happening in the Spratly Islands of the South China Sea in order to understand how it's negatively impacting coral reef communities. And ironically, while this paper was in review, one of our control reefs, a reef that we deemed unmodified, was dredged by the Vietnamese, and that's Lad Reef, and it's shown here. So thanks very much for your time. I look forward to talking during the panel period.
Thank you so much, Joe. And remember, you can ask your questions as we go with AGU emergent data. And next up, we have Robert Moorhead talking about drone data challenges.
All right. So I was asked to talk about data challenges with drones, and so if you want more information on what I want to talk about, we have a booth in the exhibit area. It's the Northern Gulf Institute booth, as opposed to the Geosystems Research Institute booth. So look for Northern Gulf. It's 546. Okay, so before I talk about the challenges, I want to talk a little bit about the advantages of drones or unmanned aerial systems. In this picture, you can see 4 all the way from a satellite down to a UAS, so you can see how much more data, how much higher resolution you can get. The other advantage of a drone is you often can fly under the weather. Second is there's a lot of missions that scientists want to do that are dull, dangerous, and you relieve a person from having to get bored and have an accident by using a drone. The third is the fourth is often more efficient, cost-effective. You get higher resolution data, and you often can do it for less money. So let me go through the challenges, a lot of them in one slide, and then I'll show you some pretty pictures, or prettier pictures. So the first thing is you have to make a decision about small, medium, or large. The advantage of the smalls is you can transport them easier, you can get up, operate in smaller areas. So if you're looking at a small area, use a small drone. By the same token, there are larger drones. I mean, there's the DoD and NASA and NOAA are using things as large as the Global Hawk. If you saw one of them on a runway, except for the fact that the windows are solid, you would not know that it was actually a drone. They're the size of a regular airplane. Second thing is the propulsion system. Most people use drones, small drones that have electric engines. They don't shake, rattle, and roll as much as a gas, but a gas motor is more energy efficient. The third thing is the design. Fixed wing will allow you to sample, measure, map at a more consistent, regular, even pace. But the advantage of a vertical takeoff and landing or a multi-rotor is that you're able to lift off from areas like roadways between forest In narrow areas where you don't have the ability to come in and land a fixed wing, it may take you 400 meters and 50 meter height to come down. So that's the advantage of a VTOL. The advantage of the fixed wing is you get about 3 times as much area coverage per unit of energy. So for the same battery, you can cover 3 times as much with a fixed wing in most cases. There are hybrids that are coming out. I'll not name names, but there's some all the way from the smalls to the large. The advantage of those is you can take off from a confined area, get up, and then go to level flight to do your sampling, come back and land in that confined area, something sometimes even as small as the back of a pickup truck. The trick with those is they're often a little more challenging to make sure you don't crash them. But we're getting there pretty quickly. I'm sorry, let me go back. Construction material. Most drones now are made of composite materials, all the way up to the size of the Predator Global Hawk or something like that. They're more durable. Foam is cheaper. It's lighter in some cases per unit area, but I think in most cases you'll find composite materials to be the better way of doing it. There are some exceptions. So you have to make a trade-off there. The foam tends to float when you try to land. Sometimes you have a hard time getting it to come down. So that's often an issue. Sensor systems. I'm going to get to this in more detail a little bit later, but it depends on what you're trying to do as to some other issues. So I'm going to mention a little bit now, and as I said, dig into it on a couple of more slides. So if you have a frame grabber, you're getting 2D data. It's like a matrix, pixels, images that you normally see. A lot of the higher end sensors are line scanners or push broom, and you're only getting one line at a time, moving forward, getting another line. That extra dimension may be spatial or spectral. And then point sensors like LiDAR or something like that, you're going to require some more add-on other than just the vehicle and the sensor. So I'll talk about those in a second. Okay, some pretty pictures. This is an ag field. This is also to try to increase Chris's point about please move forward. Some of those in the back may not be able to see that they're actually white dots from which white dashes extend, or black dots from which black dashes extend. The white dots are where images were taken. Black dots is where you really aren't going to use them within the mosaic that you're trying to create. There's colors overlaid on there, and you can see where there's a high density of white dots, it's green. That means that that's an area where you actually got enough images to where you can mosaic. The yellow is where it's questionable. The red's where you have an image, but there's not enough context around it to find enough tie points to create a mosaic, and there are even black areas where there's no images. So what happened here is, on the bottom half is where the UAV started, and by the time it got to the upper left, something had come loose, and the UAV was no longer telling the camera to take pictures. Point being, if you buy a cheap drone, you may not get reliable or robust results. But we're able to land, and there's this program that says, we got a problem. So you can refly almost immediately. This being an ag operations, you only get that vegetative state once a year. So if you don't get it done, you're going to have to wait a year. Shadows and oblique imagery. You can see here shadows. There's a much different problem, or you have a challenge here with the data versus manned aircraft or satellite, where your one image may cover 2 or 3 square miles. With your UAV, it may be more like a 300 by 200 foot image, and you mosaic them together. So you can see the shadows in this area, in this farm, where as the drone went along, the clouds blocked the radiation source, the sun, and then moved away. So you can see you get this issue as you go through. So there's a data challenge there, dealing with the clouds. I'm starting to check the volume here. So this is another challenge is you may want to do wetlands, beaches. So this is a UAV that will actually let you launch out of a boat. It's fairly large. It's a 9-foot wingspan, 5-foot fuselage. You can see the guy just throws it and it takes off. That's the easy part. Here's the harder part. Where are you going to land? You don't have a runway. You don't have grass. You've got marshes. So you land in the water. You don't have stobs. You don't have sand to tear up your lens. It's much softer. That's why on water skiers they tend to fall in the water, not on the beach. Okay? So there's a challenge. How do you image beaches and marshes well? Atmospheric is something that I think is still a research area. A lot of times you're flying a couple of 100 feet, atmosphere may not be an issue. With COAs, you can often now, with even $20,000 aircraft hand launch, you can get up, like that previous one, up to 800 or 1,000 feet. If you get up higher, you have a lot more issues with atmosphere. Where is the cutoff? Where do you have to start worrying about scattering of the blue channel, it not focusing, etc.? Position orientation. I indicated I was going to get to this. Your aircraft has a position orientation system that is smoothed. You don't want it jerking around all over the place. So it adjusts maybe every second. But if you're using a high precision or a non-frame grabber type of sensor, if your aircraft's just flying as simple or as slow as 20 miles per hour, that's 360 inches per second. So you've got to sample, if you want 1-inch resolution, 360 times a second. That's not that bad. The issue is if you're flying at 400 feet, you're flying at 4,800 inches. A 1 degree pitch, roll, or yaw will cause you to look 83 inches off a nadir. So you're trying to get 1-inch, 2-inch resolution on the ground, and with just a little bit of shake, rattle, or roll, you're going to be 80 inches off. Therefore, you need very precise positioning and orientation for things like LiDAR and hyperspectral imagers that may be push broom. Okay, I'm going to skip this for the sake of time. All right, mosaicing. Now we're getting to the data processing. So when you take these images, sometimes you get fiducials or tie points that are only partially in a frame. So in the upper left here, you can see a barrel. It's a 60-inch barrel. We've got 1-inch resolution on the ground, and you can see the tear in the image when it tries to put the barrel together, which is in a couple of images. So you also see the blurring. Okay, so it's like interpolating. I think that's what it is. So you can choose to overlay or interpolate. The general default is interpolate. On the bottom left, that's actually an ag field that I've zoomed way out. We cover that in about 20 minutes at 100 feet above ground level. There's some holes in there. The holes are from where that lightweight aircraft got buffeted by the wind. So what you can do to fix that is you go back and fly at a higher altitude. That's your most probable way to fill in the holes. Or you just refly at the same altitude, and hopefully probabilities will not happen such that you miss that area again. On the bottom right, the issue here is, much as we have problems with figuring out which blue piece goes in the jigsaw puzzle for the sky, mosaicing software needs unique information to lay everything down. The good news here is oftentimes that repetitive information is not what you want. That's not the key information. There's no alligators out there, probably. I mean, there's nothing there that's fiducial. There's no big trees or blobs of sargassum or anything like that, or else it would find it and it would mosaic it together. Cornfields are another thing where it's row after row of the same corn. If you have a problem, it'll find it and it'll fix it. Okay, the last one, and this is the one that most of you will deal with when you start dealing with drones fairly quickly, is data overload. We covered 20 square miles at 2-inch resolution in that area, which is just about an hour northeast of here. It's called the Honey Island Swamp. It's just on the other side of Slidell, Louisiana, southwest of Stennis Space Center, if you know those areas. Every other month, the issue was hurricanes had come in and disrupted the area. NOAA was interested in trying to determine how the area would recover so they could predict the next flood. That's 150 gigabytes of data per week, raw data, to cover that 20 square miles at 2-inch resolution. We now are starting to use a hyperspectral camera, push broom, one line, 20 minutes of flight. It's about 1 gigabyte per minute. So with a VTOL, we can fly 20 minutes, we get 20 gigabytes every time we try to collect data. Finally, the technology is very much ahead of the regulations. You can do a whole lot more than, for example, in the US, the FAA will allow you to do. And with that, I'll quit. Thank you.
Thank you so much. And last, so currently in the poll, citizen science is ahead for interest, but the questions are coming in on CubeSats and drones, and now we'll turn it over to Julia, bringing it all the way down to humans as sensors.
Human beings. Hi, everyone. I'm the founder of IC Change, and I thank you for having me today. I'm quickly going to run through how IC Change works in the citizen science space and how communities are using the data that can't easily be scraped or remotely sensed. In fact, by partnering and co-producing data with communities, the very process creates impact. The kind of impact that we talk about when we talk about decision makers and users and the community that we're trying to serve. So I look forward to a hearty discussion after this. Thank you very much. So we all know that extreme weather is rapidly challenging and changing how we design our cities. And the data sets and the models that we depend on to make decisions is sometimes out of date or missing crucial context or details. But even the best kind of data, even if it's perfect data, if it's not being used, then it is not valuable because we don't understand the decision-making context. Decision-making, science tells us, happens across both halves of our brain. And yet, when you think about it, science is only communicated using the logic and the linear and the data side. And yet it's this other side that we're missing opportunities in, with details and data opportunities to understand the lived experience of how extreme weather and climate are changing our communities, adding real details that people care about. So that's why we developed Icy Change. We launched it nationwide in partnership with NASA in 2015. Icy Change is a community climate and weather journal that syncs both community stories and data to personalize and track weather and climate impacts on daily life. Icy Change lets you ask questions and make observations with your phone. Your questions are synced with remote sensing data and broadcast to our network of scientists, journalists, and other citizens, allowing the entire community to investigate in real time. For example, this is Amber Kleineman from our partner community where we piloted Icy Change in Western Colorado. And she posted in 2015 in Colorado in January that her bees had woken up. The community zeroed in on what was going on very quickly after she posted on Icy Change. Silver maple flowers were blooming in January in Colorado in 2015. Totally weird. On top of this, frogs were singing, termites were hatching, and fires were burning, grass fires were burning in January in Colorado. All of these were early signals of what proved at the time to be the warmest or earliest spring on record in the West. And early springs, so again, these like small signs of change these small signs of change of spring, to city planners and disaster managers have major consequences. We know that it leads to, wildfire risk, drought risk. All of this suggests that, these are billion-dollar disasters that we can actually, if we sync all these networks together, we can actually start to get ahead on. At the end of the day, the best expert when it comes to weather and climate isn't, the app on your phone or the guy on TV or the data. It's you. It's me. We're all experts in our daily lives, in our backyards. So here's a few more examples. Someone in Northern California posted about beached whales washing up in the Bay Area in 2015. We also sync to NASA satellite data. Again, NASA was our first partner, OCO2, actually, the mission that we were talking about earlier. And we do this so that we can connect the dots between small signs of change and bigger picture trends. So at the same time, someone else posted about blue Villela jellies that they had never seen before washing up in Southern California. So the Icy Change team quickly took note and interviewed scientists who had noticed unusual pockets of warm water developing off the Pacific coast, and this was not related to El Nino. Scientists, geniusly referred to these as the blobs. Great marketing. And the blobs were not only upending marine ecosystems, they also might have been prolonging warmth and drought, the same kind of warmth that woke up Amber's bees. So we also work with media partners, and the story was reported on the local public radio station in San Francisco, KQED. And a year later, this was the cover of National Geographic. But our community was reporting it in real time. Just as scientists were trying to figure it out, citizens were could be a part of that process. So all of this is to suggest that citizen science, when combined with stories, illuminate a missing opportunity to do better decision-making in science collaboratively. And considering that weather and climate impact everyone and everything, we see multiple opportunities for real-time forecasting and impact analysis that includes the community's voice around what to monitor and how to adapt. Today, we are thrilled to have a global community. We have icy changers posting about failing monsoons before the heat waves hit. We have people posting about early springs in Australia, wildfires and drought in Canada, and flash floods you probably haven't heard of in Rwanda. And we're thrilled about this, but in order to really have impact, you really need to work at the local level. So we actually committed in 2016 to a new way of working, to connect the data that we collect to decisions that get made at the local level. We call these community investigations, and our platform brings together residents and community groups together with scientists and decision makers to co-investigate local topics that people care about. Our first was the Harlem Heat Project, which focused on urban heat. Scientists estimate that heat waves kill more people combined than all natural disasters combined, all natural disasters combined. But you have a really hard time measuring it, especially indoors. So you have to partner with communities to do that in the urban context. Then we put temperature sensors inside people's apartments without AC. They had them tell stories in sync with the data feed. So this is Helen Jones. She's close to 80, and she was telling us about her 3-month-old grandson and how hard it was to keep him happy during the heat waves. Now, these are textbook examples of those who are most impacted by climate change. This is kind of an average of what the summer of 2016 looked like. We proved that indoor heat waves behave very different from outdoor heat waves. The outdoor temperature is in yellow, and you see how it dips beneath that red dotted line. That's the 80-degree mark our bodies need to come to at rest at night. And if you see all those little squiggles, those are the sensors inside people's apartments. These buildings are trapping heat. And when we modeled it out, we realized that indoor heat waves behave very differently than outdoor heat waves. In fact, we're doing heat advisories all wrong. We need to be warning communities 4 days before a heat wave hits and up to a week after the heat wave outdoor ends. Here in New Orleans, our team launched a flooding pilot in the Gentilly Resilience District to create baseline data that can better target, monitor, and evaluate HUD-funded green infrastructure and stormwater management efforts. Again, this was a citizen science pilot that includes residents documenting their experiences alongside locally collected rain gauge data. And right away, we noticed that residents were seeing something that the rest of us weren't, that the city was flooding more, 3.5 months before catastrophic flooding hit our community in July and August, what proved to be the rainiest summer on record in New Orleans. But I'm going to tell you a little bit about this particular corner. Now, if you look at this corner in the modeled data, this is the 5-year flood model, it doesn't stand out. That's that green circle you see there, that's that corner. The pink box is where we have proposed green infrastructure planned. And if you rely on the data alone, the remote sensing data alone, to make decisions, you might think the worst of the flooding is in that deep blue spot. However, according to the Icy Change community in this neighborhood, the green circle is a major inconvenience and an intersection where everybody is flooded. School buses, garbage trucks that get caught in there and break the catch basins. It's a kind of a mess. This is Destiny Bell. She lives on that corner, and we recruited her on Icy Change. And thanks to her, we captured very detailed data on how this corner floods and drains. And we were able to document a catastrophic flash flooding event on August 5th, the picture that you see her in right now. Using rain gauges and time-lapse cameras and GPS, we modeled the event here, where over 30 cars were flooded in the neutral ground. That's what we call the median here in New Orleans. It was a hot spot on par with flooding that happened near underpasses. We also modeled the drainage. It took 27 hours for this corner to drain compared to other spots in the neighborhood, which took 10 to 12. That's a rain gauge if you haven't ever seen one. We highly encourage people to use them. This is the model data. This is the hydrograph showing relatively average events cause significant nuisance that translate to major issues during high-intensity rain events like we saw on August 5th. The National Weather Service the city's flood modelers, and green infrastructure designers have all told us that this kind of location-specific community source data is crucially important for making decisions and monitoring urban stormwater. So IC Change posts were even collected and included in a recent design RFP by the city. But we can also see incredible changes in Destiny as well. In a very short time, we see how she talks about flooding. And in New Orleans, you hear this from everybody. Every time it rains, it floods. Every time it rains, it floods. But in a relatively short amount of time, you see Destiny talking about flooding in very specific and informed ways. And by the end of this year, the IC Change team is rebuilding our entire backend to be able to host a multitude of sensors, going from IoT to city sensors to manual sensors like these rain gauges, so that we can sync community-sourced impact stories with data over time. In 2018, we're distributing 300 rain gauges in partnership with the Department of Homeland Security and Emergency Management. This is our community manager, Maris Jones. We're going to be keeping her really busy this year. And in fact, she's in the back, so if you're interested in learning more about IC Change, take a look at Maris. Wave, Maris. She has some pralines, the New Orleans candy, so please come and take some and sign up and learn about IC Change. But I did want to mention the rest of our team. We're all over the country and the world, and although IC Change works with scientists from NOAA and NASA and universities across the country, not a one of us is a scientist. We are journalists, we are technologists, and we are in service of the communities and understanding their needs when it comes to climate change. And I think that's what distinguishes us from traditional citizen science, which is often, designed by scientists in service of science. We design our platform with community questions and collaboration with scientists, with data in mind. But at the end, we focus on community members and get better results. Thank you very much. I would love to be in touch, so please check us out online and reach out. We look forward to working with you to see and discover what empowered 21st century citizens can do together. Thank you very much.
Great. So I'd like to invite our two other panelists back to the stage quickly. And so Slido, we have a bunch of great questions, but we didn't judge our time very well. So what I would like our panelists to do is to tell us where you can find them this week at AGU, because a lot of the questions we got were really specific to each of you, wanting to know the details. And so if you can just, if you've got a booth number, if you've got a talk, just quickly run through those things, or we can also post them on the Data Fair website.
The Northern Gulf Institute. Push to talk. There we go. The Northern Gulf Institute booth is 546 in the exhibit hall.
Super.
Joe's looking it up.
I am looking it up, but I turned my Wi-Fi off. Sorry.
And we can tweet these things during the awards for people.
So it's the town hall tomorrow is at 12:30 p.m. It's Town Hall 23D, Earth Science in Real Time with the Planet SmallSat Constellation. So join us there if you can. Also, you can tackle me after this. I have some postcards that can show you how to apply to the program.
Awesome. That would be super.
And we have a PDF. I'm doing something every day at AGU. I think I'm locally available to do so, and I'm thrilled to do it. If you would email us, community@icchange.org or julie@icchange.org, we have a PDF that we can send to you to follow up with us in person for the rest of the week.
Oh, I should also briefly mention, we have at least 8 talks being delivered on the normal scientific program that use planet data. So if you search for Planet, CubeSat, or CubeSat, SmallSat, you'll be able to find most of those as well.
Awesome. Can we give our speakers one more round of applause? So before we break up, and in the spirit of emerging data trends, AGU took on an exciting activity to open up fall meeting data and embrace emerging data trends and data access through APIs with an open API challenge this fall. So with that, I'd like to turn the stage over to Data Rem and Rick Moraine to announce the awards for the Open Data Challenge.
Hi, I'm Dana Rem from AGU, and we're going to take just a few minutes to celebrate the winners of AGU's first Open API Challenge. This is part of a digital transformation at AGU that is just getting underway. The goal of our digital transformation is to create a modern digital ecosystem that's focused on the needs of users, in our case particularly scientists, and that is very much data empowered. So for the first API challenge, we opened up meetings data, 3 years of abstracts from the fall meeting, and then we invited anyone who could and would to experiment, work with that data to see what they could discover. We were looking for discovery of, say, unexpected science, for opportunities for collaboration. We really didn't know exactly what we were looking for, but fortunately our developers found some things that were worthy of discovery. As we go forward with the digital transformation, we're planning to open up new data sets on APIs. And one of the things that I would like to hear from folks, if you see me around, and I'll hang around afterwards, is what kind of data sets you would like to see us open up, and in what ways and for what purposes. Once we get data in condition, we'd like to open it up and invite that experimentation again. We had a very capable head judge, Rick Murnane, who is also the chair of the meetings committee for AGU, and also a number of reviewers and judges who put in a lot of work into evaluating the application. So we want to thank all of them. I think some of them are here, and now Rick will present the winners. And I think give the check, I hope.
Thanks, Dana. And I first start off saying I really enjoyed the presentations for the earlier panelists. It was very inspiring. The data that we're using is not so nature-oriented at first, but it talks more about the people who are working with the data themselves. And so this is the basis of the prize was to basically mine the data in the AGU abstracts from previous fall meetings. And this was like a first step in a longer-term project that Dana was talking about of opening up the APIs. And my goal as the chair of the meetings committee was that this would have been an initial effort to developing an open source meeting app. And because I think the scientists who might work on this know probably better than anyone else what it is that they might want to find out of the meetings. And so there's a lot of tools that are out there that people can use. And what we will see from some of the examples, the slides that are going up here from the apps that people made, that there's a lot of good ideas that can be made, that can be good ideas associated that can be built around the data itself. So I guess I'll first call up. There's 3 winners that we have here, first, second, and third place winners. I'll call it the third place winner to start with, Jerry Rizzo. And this is an example on the website of what his app does based on some keywords that you can use to find the relationships between what the keyword is and sort of nearest neighbors in the AGU abstracts that are out there. So Jerry, if you want to come up. So this is a $5,000 check for Jerry. Okay, the second place winner is a team that was made up of Tom Narok, Sarah Hasnan, and Ronnie Stephen. And you can see an example of one of the displays from their effort up there on the slide, which actually they did a lot of stuff looking at time series of the records that are in the archives from the AGU abstract. Okay, and then the moment you've all been waiting for is the first place prize. It was a husband and wife team, I believe, developed the AGU Explorer that sort of incorporates spatial information as well as other graphical styles. And so, if they want to come up, the winners were Mina Rao and Bennett Battle. So I want to emphasize also that this, the contest was done on a very short time frame, actually. So I was very impressed by the amount of work that could have been that was done on a short time frame. And I also want to compliment our selection committee that we used for this. They're listed up here. I don't want to take the time to run through the names. We had a selection committee and we had a judging committee as well, right? Both names are up there. The reviewers. So these are the people who actually contributed a lot to this and made this whole effort possible. And I'm very excited about this effort because I think it's the first step in AGU's effort to really open up their tools and being able to combine it with other things that are out there. So thank you.
And Rick, before you go down, can you have Dana and all of the teams come up and we can have one picture with everyone up there?
Yes, we can do that.
Thank you. Thank you all for joining us tonight, and for those of you who are judges or reviewers who are still here, if you just want to come join us, join me, and we'll go from there. Thank you.